Now, to represent a vector in space, you need two things. You need one point along the not the vector. To represent, we're looking at lines. Let's say representation not of vectors, representation of lines in space. So if you have a line, like for example, this one I've sketched here. Now, to give a full description of what this line is, we need two things only. One, we need any point on the line. Just one point. We can be given multiple points, but to get a full picture of what the line is, we only need one point. Let's label this point as P. Then the second thing that we need here is a vector that shows us the direction of that line. So here, the vector can be taken as something like this. So the vector just has to show us the direction. So this vector can be taken as V. Now you have to get one thing. The vector that we have there, it's not necessarily a unit vector. It's just some random vector that points in the same direction as our line. So these two information will tell us exactly what that line is. And using these two information, we can predict where we are on that line with respect to time. So those two give us the main information that we need to specify, to give a full detail of what a line is. Now, there are three ways in which lines can be represented. Of course, we've seen that we only need two things, the direction and the point. But to actually represent a line, there are three ways in which we can do it. One, we can use what we call the vector form or the vector equations. If we're not using vector way or the vector representation, the other way that we can represent lines is going to be in form of parametric equations. And then the next one, the third one, the last one, we can represent a line in form of symmetric equations. So these are going to be the three ways in which we are going to represent our lines. Now the question is, how do we represent our lines in each of these forms? Now let's start with an example to just show you guys how we actually represent these lines in the respective forms. So let's look at some examples here. So here we have 4 examples that we can use, but for now, we're going to do the first 3, and then later on, we're going to come back and do D, because D involves a few concepts that we'll look at a bit later. Now, in the first example, they're saying they want us to get the vector equation of a line that passes in along those 2 points. So our points are, we have 1, -1, 1. And the second point is -1, 1, -1. So we have a line passing through these 2 points. How do we get the equation of a line, the vector equation of a line that passes through these 2 points? Now, remember what I mentioned when we started. To describe a line, we need 2 things. 1 point on the line and a vector in the direction of the line. Well, here we can take the point to be any point among these 2, but I'll take it to be 1, -1, 1. So we have the point on the line. The next thing that we need is a vector that runs along the line. Well, if we know that these 2 points are on the line, it implies that if this is such a line, if this is the point P, we can assume that the second point there, of course, I'm just plugging these here, but they can be anywhere really. But let's say the second point there, let's call it R, is somewhere here. Notice that to get a vector that runs along our line, we can actually use those 2 points. So the vector running along the line, we labeled it as V earlier on. So this vector can be taken as PR. So you can take this vector as PR. So all we have to do is find the displacement vector running from P to R. So how do we do that? Well, the vector running from P to R here would be Remember how we get those? It's literally what we're doing in the earlier example, but the difference is there we're getting the magnitude instead. So since this is our P and this is our R, it's the final minus the initial. So it's minus 1, minus 1, minus 1, minus 1 in the I direction, plus, then we have 1 minus minus 1 in the X direction. So that is in the J, I mean, minus 1. Is it 1? That is 1, not minus 1. That is 1 minus minus 1 in the J direction, then plus in the Z, we have minus 1, minus 1. So minus 1 here is just a 2. In the K, we simplify this, we have minus 2. In the I, then this is going to be plus 2 in the J, then we have minus 2 in the K direction. So this is our line PR. Having obtained our line PR, now we have the two details that we need to represent a line. We have 1 point. Actually, we have 2. We can just pick 1. We decide to pick P. Now, how do we represent this? Well, to represent a line in vector form, let's say this is our line. To represent this, well, our coordinate system is in terms of X, Y, and Z. Then the next thing that we need is the point on the line. Remember, it can be any point provided we are guaranteed it lies on this line. In our case, the point that lies along this line that we decided to go with is 1, -1, and 1. So that point comes here, 1, -1, 1. So this is the point that lies on our line. The last thing that we need is going to be the displacement vector or the vector that runs along our line. In this case, that vector turned out to be this one. So to represent this, we're going to pick a parameter, and that parameter is, that we're using here, is going to be t. So use t as the parameter, and then we just get the coefficients here. What we have is -2, then we have +2 here, and then we have -2 there. Okay, so this becomes the vector equation for that particular line. So this is basically how we get these expressions. Any question there? Okay, so looks like we do not have any questions there. Yeah.
Representing lines is that vector representation, parametric, or which one?
Okay. So this one here, this is the vector representation.
Okay.
So this is how we represent vectors, lines as a vector. Now, before we look at the other forms, we have this next one here. For this one, they're saying that we have a line that passes through this point and moves parallel to a line to this vector, not the line. It moves parallel to this vector. Now, what does it mean when a line and a vector are parallel? What does that tell us about their direction?
In the same direction.
They are in the same direction. They have the same direction. So getting line 2 will actually be straightforward. Again, if we're dealing with X, Y, and Z as the coordinate system. So the first thing that comes is a point along this line. What point are we going to use here?
The first one, 1, 0, 3.
Yeah, so here we're going to use 1, 0, and 3. Then for the parameter here, we can switch them. Since I'm using t for the first one, let me use n for this one. And here, remember, this is where we plug in the vector along the line, or the vector that has the same direction as our line. And in this case, this vector, since it is parallel to our line, it means that that is the one that we use. So you have 2, -1, and -1 as well. So this becomes line 2. Is that okay? You can try to do the same thing with C there. The only difference with C is that, look at that vector, the one we are moving parallel with. That vector is just given as minus k. What this, of course, should tell you is that we have 0j, and then we also have 0I. So this is the vector now. In the x, we have 0, 0, and then minus 7. So that is what we are doing with that one. So, of course, the treatment becomes the same to how we treated b there. So this is how we represent lines in vector form. So the next thing that we have to do is, how do we represent lines in parametric form? So we now want to get what we call parametric equations. Okay, so this is what we're going to get now. Well, if you can get the vector equations, getting the parametric equations from the vector equations is going to be very basic. Let's pick the first example, the first line that we had. So if you have a line like this one, and then you want to get the parametric equation from this line, how do you do it? Well, here's the approach. So we'll use examples to understand this part. The first example, we have this line, want to get the parametric equations of this line. So to get the parametric equations, easy, just equate the corresponding components. Like, for example, on this part, this is the x part. And from this one, the x part is this. From the third one here, the x part is going to be the minus 2 here, but we'll multiply it with the t that is outside. So in other words, for the last term here, the t will be distributed inside. So we're going to have minus 2t, then 2t, then minus 2t as well. So how do we do that? So first, the parametric equation in terms of x will be x is equal to 1. Then we have plus this one here, which is minus 2t. So this becomes minus on the middle, then we have 2t. So this is the first parametric equation. The next one is in terms of y. Well, what will y equate to? Y will relate to -1 there. Then can you guess what the last one there will be? The plus what?
2t.
2t. And the one for z, can you give me the whole equation for z? Z is equals to?
1 minus 2t.
Yes, 1 minus 2t. So these are the parametric equations. Clearly, you can tell that if you can get the vector equations, getting the parametric from the vector is very, very basic. Look at that second line that we did. The second line we had was this one. Now, how do we use that to get the parametric equations? So this will be our example 2. So if the line that we have has been described in vector form again, in this case, I'll go through this very quickly because of you guys are able to do it. X is equals to 1, then this becomes plus 2n. And then we have y is equals to, this is going to be 0, plus, that becomes minus because this is minus 1. So it becomes minus n. Then lastly, we'll have z is equals to, now that's going to be 3 minus n there. So these become the parametric equations there. Don't have to label them like this. If the question says find the parametric equations, just find them like this, and then you're good. So any questions on parametric before we go on to the last form, symmetric? So to get the symmetric equations, again, if you have the parametric equations, getting the symmetric is going to be very easy. Later on, I'll show you how to move from vector straight to symmetric and vice versa. But if you have the parametric, getting symmetric is going to be very basic. Now, what happened? Let's use these questions again, the ones we just obtained, as our examples. So what are we doing there? So in our first example, our line is represented in symmetric form already. not symmetric, in parametric form. So you have a line L1, which is given in parametric form. Now, what we want is to represent this line in symmetric from parametric. Now, the question is, how do we approach that? So all that we have to do here is this. Get each parametric equation and make T the subject of the formula. What this implies is that from the equation for X, when you try to make T as subject, we're going to end up with T is equals to the 1 moves the other side, so that we have X minus 1, and then we have to divide by what? Both sides? What are we going to divide by? -2. You see that? We have to divide by -2. So this becomes what comes out from the one for X. Let me do the one for Y a little bit slowly. So the one for Y, what we have is Y is equals to -1 plus 2t. So we move -1 to the left, it becomes positive, plus 1 is equal to 2t. Then divide both sides by the coefficient of t. So that now we remain with the expression t is equals to y minus 1 or plus 1 over 2. In the same way, we do the same thing for the z expression. And if we did that for the z expression, what we're going to have is t is equal to, can you see it's z, then what? It will be z, then?
-1.
-1, then?
Negative over -2.
Over -2, yes. So these become the 3 expressions. T here is x minus 1 over -2. Now, these are the expressions that we use to make the symmetric equations. Observe that the 3 equations both define what t is. So since they are telling us this what t is, and since these are coming from the same expression, it implies that the value of t here must be the same. Therefore, we can equate them. So it then goes on to conclude that we have x over -2. This has to be the same as y plus 1 over 2. And this also has to be the same as z minus 1 over -2. This becomes the symmetric equation. Let's look at the second one, just to help you guys get a full picture. Again, picture this one where we have the parametric equation already. How do we use the parametric equation to get the symmetric? So this is example number 2. So in this example, what is happening? Well, just like before, we just have to make n the subject of the formula. So if we make n subject on the first one, we're going to have n is equals to x minus 1 over 2. On the second one, we're going to have n is equals to, can you guess, n is equals to what?
Equals to -y.
Yeah, but we don't really want to say -y. We kind of want to say y over -1. In fact, you might even say y minus 0 over -1, just to show everything that we need there. But yes, I get why we're saying -y, because the one divided up there, right? But we'll keep it like this. Then the next thing here, we'll make n subject on the last one. If we made n subject on the last one, it's going to be n is equals to, it will be z minus 3, then divided by -1 again. See, we can easily evaluate the -1 and take it up, but we want to leave it in this form. Why? So that this keeps having the same setup every time. X minus 1 over 2, observe that the variable is always positive. Even here, this is equal to y over -1, again, the y there is positive, equal to z minus 3 over -1. Again, observe this is positive there. If you end up with a scenario where this here turns out to be -y, of course, it should click in your mind that most likely what is down here is not 1. It is in fact this negative. It's not for the y. The negative is for the 1 down here. You get that? So this becomes the symmetric equation for our line 2. So these are the symmetric equations. Now we have looked at all 3 types of representation: symmetric, vector, and parametric. Now, I showed you how to move from vector to parametric, then from parametric to symmetric. Now, what I want you to observe are the similarities, so that hopefully you will be able to move from vector directly to symmetric without having to pass through that to the parametric form. Now, let's compare the two. Let me get the vector equations and compare them to the symmetric equation. This is for line 2 in vector form. Then we also have line 2 in symmetric form. This is the one here. So this is the same line. The two expressions describe the same line. The only difference is how we have represented them. In the one in red, we have used the vector form. In the one in, let's say, blue, what we have used is the symmetric form. Observe how they are relating. Observe that firstly, the denominators here, look at where they're coming from. They are coming from the vector here, the vector giving us direction. It's 2, -1, -1, exactly with the sign. Have you seen that? Yeah. And then lastly, notice that you always have the variable x, y, z, which is in relation to the variables that you have here. Had this been maybe nm and so on, something else, those would have been the variables being there. And the last thing is this. Observe these numbers here. -1. Here we have a 0. And then here we have -3. Notice that they have something to do with the numbers which are here. But can you observe the difference?
Or subtracting them.
Yes, we have swapped the signs. If this is 1, when writing the symmetric, it becomes -1. We subtract it. If this is 0, of course, we have -0. If this is +3, we subtract it there, it becomes z -3. That is how we move from the vector equation directly to the symmetric equation. Is that clear?
Yo, Jeff, I can't see your screen.
How about now?
Thank you. Okay.
Okay. Yeah, so basically that is what is happening there. So just the signs have swapped up, and then we end up getting the symmetric directly. Okay, any questions on the representation, or we can move on to something else?